We verified the net list. Then we insert the test logic. It's called DFT, designed for testability. There could be different kinds of faults like stuck at 0, stuck at 1. So we want to make sure that there are no fabrication faults. We design the chip, then the chip will go through physical design flow, and then whatever the netlist we are going to generate, GDS2, we will ship it to foundry. The foundry will fabricate the chip. But after getting the chip, the silicon, we are going to check whether there are any fabrication faults. There could be various fabrication faults like stuck at 0 and stuck at 1, or there could be open circuit, there could be short circuit. How are we going to verify the silicon? That's where we follow DFT, designed for testing or testability. As part of DFT, what we do is basically we insert the test logic so that we would be able to detect the fabrication faults later. So what we do is we replace the flip-flops by scan flip-flops, something like this. So here you have different options like normal mode and test mode. During normal mode, you can run the simulation as we expect. This is going to be the usual design at RTL, register transfer level. But during test mode, you would be able to skip the combinational logic and connect all the flip-flops like scan chain. So what we do is we inject a stream of bits, and then we make sure that the same stream comes out. So we make sure that all the flip-flops work fine. This is called scan chain. So we would be able to run the chip on different modes like normal mode and test mode. So after getting the silicon, we would be able to inject the stream of bits, and then we would be able to test the chip. Also, there are different techniques like test compression. So basically we follow algorithms like ATPG, automatic test pattern generation, to generate the manufacturing tests. And whatever the test patterns generated by the EDA tool, ATE, automatic test equipment, will make use of all the test patterns to test the chip. So after getting the silicon, what we do is we make use of the ATE, automatic test equipment, to inject the test patterns. Also, ATE is going to compare the output from the chip with the response. And to deal with the data, all kinds of test patterns and the responses, what we do is we follow test compression so that we compress the data and ATE can deal with it efficiently. So automatic test equipment is the one we use to test the chip. Also, we follow techniques like boundary scan. It's primarily used to verify the connections between the chips on the board, or it could be like connections between the subsystems within a chip. And there could be various other things like BIST, built-in self-test. It enables the chip for the testing. So there could be various things like logic BIST and memory BIST. So what it means is actually the chip itself will have all the components. You don't really need to depend on ATE. The logic will generate the necessary test patterns, and then it will make sure that the chip is working fine. That's called built-in self-test. So this is what actually you are going to explore as part of design for test. So there could be various DFT tools. So what we have seen is the front-end design flow, spec to synthesis. Spec to synthesis, it remains same for FPGA. Whether you are going to implement the design using ASIC or FPGA, front-end flow remains same. And for FPGA, we don't prefer DFT because the silicon is pre-verified. You are going to buy the chip directly from the vendor. So if you want to implement your design on FPGA, what you would do? You would be talking to companies like Xilinx or Altra, and they work with the foundry, and then they fabricated the chip, and they have tested the chip also. You don't really need to worry about DFT. So you just need to follow the spec, implement the RTL, you need to verify the RTL, and then you have to synthesize it, and then you need to download the design into the chip. And how to implement the design on the chip, that's where they provide the implementation software. That's how FPGA works. Now, we are exploring the ASIC design flow. Look at the physical design flow. It starts off with floor planning and placement. So as part of the floor planning, we decide the shape of the blocks and how we can decide the structure of the entire chip and how we want to dedicate space for different blocks so that the connection between the blocks can be implemented efficiently, right? That is floor planning. As part of the floor planning, we also make sure that the block is manageable. Suppose if the subsystem is going to be very complex, then we try to partition the subsystem into multiple blocks so that the number of connections between the blocks could be less, right? And as part of the placement, we decide the exact placement of each block and subsystem, and then we make sure that the connections can be implemented efficiently. How are we going to connect the blocks with the external pins, the placement of I/O pads, everything. Then we take the design through clock pre-synthesis. So we face some challenges like clock skew. If the clock is going to reach different flip-flops at different times, then we need to take care of clock skew. We expect the clock to reach all the flip-flops at the same time. Then we follow different clock trees like I-type, X-type, and H-type, and then we make sure that the clock is reaching all the flip-flops at the same time. So we take care of clock tree synthesis, and then we take the design through routing. As part of the routing, we make the connection. While making the connection, we make sure that the wire delay is less. Also, we make sure that there are no congestion hotspots. So that's the main goal of placement. And after making the connections, we would be able to calculate the exact delay between the blocks, so we can perform timing analysis. So static timing analysis, as part of STA, we make sure that there are no setup time and hold time violations. For example, we make sure that the data is stable during clock edge. If there are any setup time and hold time violations, then we make sure that the design takes care of the setup time and hold time. So during STA, we make sure that there are no setup time and hold time violations, and then whether we are able to achieve our frequency, performance. So we calculate the clock period, whether we are able to accommodate the setup time and hold time comfortably, whether the propagation delay is minimal. Suppose it's not possible. We have done everything. Floor planning, placement, and routing. Now we know the exact wire delay. During the estimation, as part of synthesis, actually, we were able to calculate the frequency and we were fine, but now we are not able to meet the frequency. Then we need to try some more optimizations as part of physical design. Maybe as part of floor planning, whether we can rearrange the block, or maybe as part of placement and routing, whether we can do the connection differently, and we can try different kinds of optimizations within physical design in the backend flow. If we can meet the frequency well and good, otherwise we have to go back all the way to front-end design flow. And then we need to make some modifications in the architecture. If we make any modifications in the architecture, then we have to rewrite the RTL and we need to repeat every step. So it's going to be time consuming. We have to avoid this kind of respin. All right? There could be various kinds of STA tools. We verified the timing. Now, we extract the layout. This is how you can visualize the layout, like stick diagram. And we apply DRC as part of physical verification. So whatever the layout we have generated using EDA tool, we make sure that the layout works fine as per the Foundry rules. So Foundry defines DRC. For example, if you are going to work with a particular Foundry like TSMC, and then you are targeting a particular technology like 3 nanometer or 5 nanometer, then you will get DRC, design rule check files from the Foundry, and the EDA tool is going to verify the complete layout based on the DRC, design rule check. So what actually it does is actually it makes sure that there is enough space between the metal layers and everything is measured in terms of lambda. Lambda is nothing but the technology. It's based on the node, 5 nanometer or 3 nanometer. And that's what we do as part of physical verification. So we implemented the layout, we verified the layout, and then finally what we do is, once again, we verify the layout with the schematic, LBS, layout versus schematic. So whatever the layout we verify as part of physical verification, right, that is the final layout. And before sharing this layout with the Foundry, what we do is we compare this layout with the schematic generated by the synthesizer, whether the routed netlist is same as schematic netlist. So LBS tools compare the layout netlist with the schematic netlist, and then it makes sure that there are no differences, and then finally we share GDS, manufacturable layout, GDS, graphic design system. Look at here. After doing LBS, layout versus schematic verification, we generate the verified GDS2, the final netlist. It's called a routed netlist or manufacturable layout. We share this netlist with the Foundry. This is the flow we follow for ASIC. So we define the design flow like front-end and back-end. Spec to GDS2 is the complete design flow. Spec to synthesis, it falls under front-end design. As part of front-end, we verify the functionality. And as part of the back-end, we verify the timing requirements of the design. So we start from the spec. Architects define the product specification. We partition the spec into hardware spec and software spec. We chip designers refer to the hardware spec, and we implement the chip. Before implementing the chip, modeling engineers implement the functional model. And chip architects, they define the architecture, how the chip is going to be. Block diagram, the microarchitecture of specific subsystems. Everything is defined as part of the architecture. And then the modeling folks implement the functional model, and that's going to be the golden reference for chip designers and verification engineers. Chip designers use HDLs like Verilog and VHDL. They implement the synthesizable model and they synthesize it. When it comes to creating synthesizable model, they focus on power, performance, and area. They make sure that it's synthesizable. When it comes to verification engineers write test bench. They focus more on automation. The test bench is going to generate stimulus. They will also make use of the functional model. They instantiate the functional model. They instantiate the design. The functional model is going to produce the expected value. The design is going to produce the output. The test bench is going to compare the design output with the expected value. That's how the test bench is going to verify the design. And verification is very complex, time consuming. They have different approaches like block level verification, subsystem level, and chip level verification. And they use languages like system verilog and methodologies like UVM. They make sure that the design is bug free. They verify the functionality. And once they confirm that the design is bug free, they approve the design for synthesis. And then the designers will synthesize the design. And whatever the netlist that's generated, DFT engineers insert the test logic designed for test, designed for testing or testability. They insert the test logic so that we can perform the testing on the silicon. There could be various fabrication faults like stuck at 0, stuck at 1, or open circuit or short circuit. So we want to make sure that silicon works fine. So whatever the silicon we are going to get from the foundry, after doing everything, right? We share GDS2 with the foundry is going to fabricate the chip. Once we get the silicon, how are we going to do the testing? That's taken care in this phase, designed for testing. How do we perform the testing? Basically, we make use of the equipment called ATE, automatic test equipment. And EDA tools use ATPG, automatic test pattern generation. EDA tools generate the test patterns, and then ATE will inject the test pattern to the chip, and then it will check whether there are any fabrication faults. So it's our responsibility to identify the defective silicon. We have to remove the defective chips, and then we need to ship only the working chips. That is called testing. All right. Then as part of the physical design, we create clock tree. We make sure that there are no clock skews. And then we create the layout. We do various things like floor planning, placement, and clock tree synthesis. And then we make the connection. After making the connection, as part of routing, we perform STA, static timing analysis. So as part of physical design, we verify the timing requirements. Are there any setup time violations, hold time violations? Whether the entire chip works fine. Are we able to target the particular frequency? Whatever the frequency we estimated during synthesis, are we able to achieve here? That's what we do as part of static timing analysis. And then the layout we generate, we verify the layout once again. It's called physical verification. It depends on the technology we target, whether we want to use 24 nanometer or 5 nanometer or 3 nanometer. Foundry defines DRC, design rule check. And the EDA tools make use of the DRC files to verify the complete layout. It's called physical verification. And then finally, we confirm that the layout is perfect for this particular technology node. Finally, what we do is LBS. The final layout will be compared with the schematic generated from synthesis. And there are no differences because whatever the schematic we generated as part of synthesis, it has gone through various steps again as part of physical design. So we want to make sure that there are no changes in the design, right? So this is also equivalence checking. LBS tool compares the layout with the schematic. Then finally, we share GDS2 with the foundry, and the foundry is going to fabricate the chip. Let's also look at AMS design flow. You can expect some analog IPs like analog to digital converter or digital to analog converter. So the chip is going to have pretty much 70 to 80% digital components and remaining 20 to 30% analog components. It's called analog mixed signal design. So in this case, what we do, we follow analog design flow. We take the analog spec, we create the layout manually, we simulate it, we verify the analog component works fine. And for the digital components, we follow the design flow, whatever we have explored. The spec, architecture, behavioral model, RTL coding using HTL, and then verifying the RTL using test benches. We follow the same flow for the digital components. This doesn't work for analog components. We have to create the layout manually. And then what we do is we also create functional models for the analog components. If it is going to be 20%, for that particular analog IP, we also create functional model using Verilog. Verilog has flavor for analog, but that's only for simulation. We can't synthesize it, right? So we make use of this functional model for the mixed signal verification. So we have the RTL components, and then we have the analog components. So for the RTL, we use HTL. For the analog, we use the analog version of the HTL. And whatever the RTL we define, it's synthesizable, but the analog model is not synthesizable. But we instantiate everything together as part of the test bench, and then we run the simulation. It's called mixed signal verification. Only for simulation, we make use of the model. So here we follow synthesis, and we generate the netlist. But when it comes to analog, actually we create the layout manually, and whatever the layout we create, eventually it's going to be part of the final layout. So what we do is, we define the layout with analog macros. So here, if you look at the layout we define, it's going to have kind of analog macros as black box. It will not have any netlist. So the EDA tool will skip those macros. And whatever the netlist we generate as part of the analog design, that netlist will be included as part of the macros. So eventually, the physical layout will have everything. Digital design components, analog design components, the complete transistor level layout will be available. This is how you can visualize. And then the complete layout will be verified through physical verification. This is how we deal with analog mixed signal design. So we start from the spec, and then we partition the spec into digital and analog. You can expect 70 to 80% digital and 20 to 30% analog. So we partition the spec into digital and analog, and we follow the design flow, front-end design flow for the digital component. For the analog, we implement the layout manually. But for the simulation, we can also make use of the HDL to create the functional model only for the simulation. So how we visualize the chip, the same way we would be able to run the simulation. That's called mixed signal verification. Synthesis is possible only for the digital component, but for the analog component, we have to create the layout manually. It's always going to be full custom. And then during physical design, we would be dealing with analog macros. They are like black box. The EDA tools, they are going to ignore the analog blocks. And then after generating the layout, we would be able to insert the analog macros. The final layout will have everything, both digital and analog. And then whatever the layout we create using both analog and digital, analog mixed signal layout, that will be verified through physical verification. And then we will also take it through LBS, and then we generate GDS2. GDS2 will have the transistors for both analog and digital components. That's how we deal with analog mixed signal design. Thank you.